But before that, let me give you another proof of theorem of Lasker and Noether about primary ideals. Well, it would be, last time I tried to do geometric proof, but in fact algebraic proof seems to be simpler. At least the last time the proof had gaps. Okay, so let me remind you the subject, definition. You define, so suppose that I is an ideal. You define radical. Is a set of all x in R such that x power n belongs to I for some n. So it's an ideal which contains I, and the typical example is when you have I is an ideal, say maximal or prime ideals. You can take I squared, and then radical of I squared is I. This explains the notation. Now I is primary if its radical is prime. And I'm going to tell you the theorem of Lasker and Noether about primary decomposition. Before I do that, let me tell you another characterization of primary ideals equivalent to that, and it's elementary. So claim I inside R is primary if and only if for each x and y in R such that x, y belongs to I, either x power n belongs to I or y power n belongs to I for some n very big. So proof, well, you need to do both ways, so let's assume that this assumption is true. Suppose that for all x and y inside R, such that x, y equals 0 or belongs to I, either x power n belongs to I or y power n belongs to I for n very big. I am going to prove that then the radical is maximal, prime. Then, okay, so suppose you have x, y, which belongs to radical, to square root of I. This implies that x n, y n belongs to I by definition. Okay, and then we can apply this assumption and get that x power m n, yeah, belongs to I, apply this, or y power n m belongs to I. Well, this because it's square root. So this, yeah. Yeah, and this implies that x or y belongs to the radical. So this is really a prime ideal because of that. So we increase our power a bit, but it doesn't matter because the assumption is that for some very big power. Okay, so the converse direction. So step 2. Suppose that radical is prime. And we have x, y belongs to I. Then x, y belongs to the radical because I belongs to radical by definition. This is the definition. And it is prime, so this means that x and so that x belongs to radical or y belongs to radical, and this is precisely equivalent that xn belongs to I, and is precisely equivalent to yn belongs to I. So this direction is even easier, you don't need to increase the power. Clear? Good. Now let me define irreducible ideals. This is analog of irreducible subvarieties, but in the language of ideals. So irreducible subvarieties are subvarieties which can decompose into a union of bigger varieties. And what is the union of subvarieties corresponds to intersection of ideals. So the irreducible ideals which can be decomposed onto intersection. So definition, suppose you have ideal in a ring, decomposition is just representation of this ideal as intersection of other ideals. And it is non-trivial if I, k are not equal to I, and also we don't want them, I mean, it makes no sense to add terms which belong to each other, so I assume that I, k not, doesn't lie in, well, yeah, doesn't lie in I, k prime for all k and k prime not equal to k prime. Okay. So this is our conditions for decomposition, and I is irreducible. Well, I would also assume that the number of these ideals, so it's numbered from I equal 1 to n. I would assume that n bigger or equal than 2. Just to make sure that this is an non-trivial decomposition. If I is irreducible, if I has no decompositions, can't be decomposed, doesn't admit a non-trivial decomposition. Now the theorem which I'm going to tell is that every ideal is similar to what we had for the subvarieties, and the proof is almost entirely the same. In fact, you can adapt like proofs from varieties to ideals, from ideals to varieties. That lemma, and it, of course, like with varieties, it takes Noetherian. So if suppose that R is Noetherian, which means that all chains, increasing chains of ideals stabilize, and I is an ideal. Then I admits an irreducible decomposition. Which is decomposition I is equal intersection to I k, where all ik are irreducible. Proof. Well, proof goes by absurd. Suppose that not all ideals assume that not all ideals admit this decomposition. Such decomposition and then we take R is a set of all ideals not admitting a reducible decomposition. Set of all such ideals not admitting reducible decomposition, and by stabilization of increasing chains, every set of ideals has an ideal which is maximal in the sense that it doesn't belong to any other ideals in the same set. So I is an element of R, so it's an ideal which doesn't have a decomposition, is a maximal such ideal. Okay, then I is not irreducible because irreducible ideal has a reducible decomposition. Not irreducible because then you take just I is equal I, this will be your irreducible decomposition. And this implies that I is a non-trivial intersection, so it's I intersection of ideals ik. Well, we don't know if they're irreducible or not, but what we know definitely is that I is strictly smaller than ik. This is our definition of irreducibility. But then all ik admit irreducible decomposition. Irreducible decomposition because they are strictly bigger, and we know that there are no ideal in R which is strictly bigger than I, which implies that all ideals which are strictly bigger already have a irreducible decomposition. Then I is equal to intersection of ik, and which is equal, each ik has a reducible decomposition. Ik is intersection of ikl. So this is intersection of ikl, which are all reducible. So we obtained an irreducible decomposition for I given a contradiction. Okay. So this is irreducible decomposition. So by this argument, every ideal has an irreducible decomposition. Am I clear? Okay. Now the next lemma is that every irreducible ideal is primary. So this was lemma. Let I inside R be irreducible ideal, then I is primary. I will use this lemma which I have written in the first slide, which tells us that primary ideals have the following property. Suppose you have x, y equals 0. Oh, sorry. Well, I would assume it suffices to show. We will replace R by R quotient by I, and need to show Okay, so then radical of well, we need to show that for each x and y which belongs to this R, if x y is equal 0, this implies that x power n y is equal 0, or y power n is equal 0. In fact, both conditions will. Sorry?
Is it lemma true in the other direction?
I think so, yeah, but I didn't check. I forgot. I was going to check, but I didn't. It's a good exercise to check whether, so exercise, suppose I is primary. Again, in the Noetherian ring. Prove that I is irreducible, or find counterexample. I think there are counterexamples. I think you can find even things like okay, not sure. Good, so let's now prove this lemma. We need to show that irreducible ideal is primary. So proof. It's step one. I'm continuing the proof. So denote by, this is annihilator. I would use the Gothic, big Gothic A. This is the set of all z inside R such that z x power n is equal to 0. It makes sense for all n, and this chain gets bigger and bigger. So you have annihilator of x belongs to annihilator of x prime, x square. It sits inside annihilator of x third, and so on. And any such chain should stabilize. So we can assume that a power of xn is equal to a of xn plus 1 by Noetherianity. So for some n which is very big. Okay. Now step 2. So we have two ideals, x power n and y. This is ideal generated by x power n and y, and this ideal generated by y, and I claim that this intersection of these two ideals is 0, which is impossible unless one of them is 0, and which would imply that x power n is 0. Because I is irreducible. Okay, so let's prove this. Suppose we have A inside this intersection. We want to show that A is 0, so it's A belongs to x power n intersected with y. This means that A is B times x power n. Okay. And also Ax is 0 because A is y times something, say z, and xy is equal 0. This is because A belongs to ideal generated by y. So this means that B belongs to the annihilator of A of x power n plus 1, because B x power n, this is the same as A. If you multiply it by x, we'll obtain ax, and this is 0. Okay, but this is ideal is the same as this. So this is the same as A of x power n. And this implies that B x power n is 0. Because B belongs to that, this means precisely that B multiplied by x power n is 0. And this in turn implies that A is equal to 0, which is something we wanted to show. Okay, so we're done. We proved that every irreducible ideal is primary, and the corollary obtained this famous theorem of Noether-Lasker. Which says that every ideal I is intersection, has a primary decomposition. It is an intersection of primary ideals, of course assuming that I is an ideal in a Noetherian ring. Okay. So this was something I did I tried to do last time using geometry, but I think this is more clear. Now I'm going to rephrase and repeat parts of what I did last time in compressed form about group representations. Okay, so definition. Group representation is an action definition. If G is a group, and V vector space, and suppose that G acts on V by linear maps, which means that G is mapped homomorphism into GL of V, then V is called representation, G representation. Okay, typically you have vector space over a field, and the category depends on the field a lot. So what is the category? We need maps, so morphisms, objects of this category, of the category of G representation, is the same as representations. So vector spaces with group action. And morphisms of V to W, from V to W is the space of G invariant linear maps. Phi from V to W, and G invariance means that, so this is phi This is d w phi again, and this is g inside g, and this is the same g. So this should be commutative. This precisely means that your map is G invariant. It is invariant under adjoint action of G. So this is a category. Clearly, if you have composition of maps which are satisfy this property, commute with G action, or compatible with G action, composition is also compatible. So this is a category. Okay. So last time I told about exact sequences. I'm repeating it very briefly. So, and I'm doing that only for representations because we need it only for representations today. So definition, suppose you have 0 goes to A, goes to B, goes to C, goes to 0, is the morphisms. So this is, let's call this I, let's call this J. Morphisms of representations. And suppose that kernel of J is the same as image of I, and image of I small. I is injective. So this is an injective map, and J is surjective. Then this is called exact sequence. Is called exact sequence of representations. So from homological point of view, this exact sequence is trivial when it splits. So when it splits, let's define. So star splits if there exists a J invariant map of G invariant map phi from C to B such that you take composition of phi with J. It will be a map from C to itself, and it should be an identity map. In other words, this is what is called a section of the projection from B to C. So you can view that as you do with, so you have C, B is a vector space. It's projected to C, which is also a vector space with the fibers which are vector spaces. And for each point of C, you want to have a point in B which is projected to this point. So this precisely means that you have a section. So when you do that for sets, the section exists for every surjective map, and this precisely is the condition of axiom of choice. So if you want to do it for vector spaces, you can always have a section, because you can just take a basis downstairs in C and just take for each basis, choose any of its preimages. For each vector in a basis, to take any of its preimages, this would give you a section of any surjective map of vector spaces. But for instance, if you have topological vector spaces or representations, you can't expect that your section exists. In fact, last time I gave an example which when it doesn't exist because of, well, it was like a Z action on R2. Doesn't have a section.
I think that the order in the position should be also.
It depends on the way you think very much. It's a good point. I think I told that several times, but I tell it again, that when I write order, it's what's called diagrammatic order, because it's what you do in categories. So you have a sequence A goes to B, goes to C, In categories, it's more logical to write J equals, it's I goes the first map, and this is J, then you write I times J, which is not the Leibnizian order when you use it in opposite direction. I can do it in opposite order, but then I would do errors. It's sorry. So to avoid confusion, I would just do it every time. Sorry. Okay. Yeah, you're right. It's opposite to what people expect. Thank you for pointing this out. Okay, so what else can we say about section? That is, if you have a section, you can take decompose B as image phi of C, direct sum I of A. Indeed, every vector, because x, if you have x and b, x is x minus phi of j of x belongs to both of these vectors are mapped to the same vector if you do projection to C, because phi is a section. So for j of this is 0. And this means that this vector, x minus phi of j of x, belongs to A. And this is why you have this decomposition, because this belongs to phi of x. So this exact sequence, in fact, decomposes onto a direct product if and only if it's a split. This is why it is called split. This explains the term. Okay. So now let's tell something. I told it last time. I will do today a slightly different proof of the. So, but this is the first, as I said, an exercise. Suppose that rep G is category of finite dimensional G representation, G representations, and suppose that any short exact sequence in rep G splits. This is what we'll prove today with respect to finite groups. Then every representation is semi-simple. Well, semi-simple representations were defined last time, and they were defined on the previous slide as well. Here. So irreducible representation are representations which don't have sub-representations. And semi-simple, V is a direct sum of irreducible. Okay. Do you want to do this exercise? You can. I don't force you. Okay. So should I tell it or should I leave it for? I did last time, so. Okay. Oops, sorry. Now I am going to tell about the category of finite group representations, proposition. And here we assume finite dimensional representations. Now we don't even need that. So suppose that G is finite group. And 0 goes to A, goes to B, goes to C, goes to 0 is a exact sequence in the category of representations of G over a field K, where K is a base field and characteristic of K coprime with the order of G. Then this exact sequence splits. So every exact sequence splits for finite groups, and like characteristic 0 or coprime with, it's the same. Last time I did it using the metric, which is geometrical, but today I would do slightly more algebraic argument, which is at least more potent in the sense that you don't need a special field for that. It works for all fields. So proof. Step 1. So you have your exact sequence, and then you can have a section in vector spaces. So suppose that Zi is a basis in C. Well, if C is finite dimensional, you can have it for free. If it's infinite dimension, doesn't matter because you still have it by its own lemma. So basis always exists. And then you can take Z tilde inside B elements, vectors, which are mapped to the basis, such that J of Z tilde, Zi tilde, is Zi. So you have your projection, and you, for each vector, you find something in the fiber. It always exists by axiom of choice. Okay, now you can have phi from C to B. So define a map. To define a map, it's necessarily sufficient to define it on a basis. If you have a map on a basis, you can extend it to all linear combinations for free. So we define phi of Zi is equal to Zi tilde. Then, by definition, J of phi of Z is Z. So this is a section. But it's a section in category of vector spaces. It's not a section in category of G representations because the way we constructed this map has nothing to do with representation. It just doesn't see the structure of representation. It's just constructed in vector spaces. So what I proved is that every exact sequence of vector spaces splits. Good. It's not enough. So we need to modify step 2. Need to modify phi such that phi is compatible, so G invariant. Okay, so what does it mean, G invariant? We have a space, gamomorphisms from C to B. And we have G action in this space. G acts on this space by taking homomorphism. What is my notation? U. So you have G inside G, you have U inside this homomorphism space. Then U of G, G of U, takes a vector V and puts it to G of U of G minus 1 of V. This agentation, so this is, yeah, from this picture, it is clear, it's a standard commutative diagram, it's clear that phi is, so U is G invariant, U is G invariant. This happens if you take, you start with, so you have your, say, C, B, this is U, this is G, this is G, this is U again. So you want U times G to be equal to G times U. And this is the same as U is equal to, in that notation, G, U of V is equal to G of U of G minus 1 of V. Just put G from one side to the other with minus, with invert, like multiply both sides of this equation by G minus 1. Okay, so what it implies? It implies that we need a section which is invariant under this action of the group on this vector space. Okay, this is now step 3. On the next slide. So we already have a section. Phi, it's not good enough because it's not invariant. Let's make it invariant by applying operation averaging with respect to a group. Average of with respect to a group of phi is 1 over absolute value of G, over order of G, sum for all G inside the G big. And here you take phi, G of phi of G minus 1. So you take an orbit of the group action on the space of homomorphism from C to B. And you take this orbit and you average over this orbit. The result is clearly invariant under group action. I mean, every time you have a group action, you take its orbit, you average or sum the points in this orbit. This will give you element which is invariant, because if you act by G on this set of all these terms, G just exchanges them, rotates them. So it fixes the set. So it fixes its sum. Okay, so this is G invariant. Okay, it remains to check that it is a section. So suppose start with, we need to check that J applied to sum of for all G inside G, G phi G minus 1 of V is equal to V. Okay. So first we can exchange J and G because G is already J invariant. So instead of having J here, we can write J there. And then you notice that J phi is equal to identity. J of phi of something. It's not it's Leibniz order. Anyway, it's equal to identity, so you can erase this. And you obtain G minus 1 of V, and this is clearly equal to V because these terms cancel. And then you have 1 over order of G, and this is the sum of the terms which are precisely G term, or order of G terms. So this is why we need 1 over G. Of course, 1 over G doesn't always exist. Namely, if you have a finite field or field of finite characteristic, and your order is not invertible in that field, it can be 0. So then this won't work. And this is why I needed this assumption that you have a field which characteristic of prime with the order of G. This is where we use this assumption to define this averaging map. Okay, so we constructed a section which is I mean, this is this new map, average of phi is a section, and G invariant, so we are done. This implies that this exact sequence splits. As a corollary, well, you can't expect that this would be true for reducible decomposition would hold for infinite dimensional representations, but for fine dimensional, this is something we have in this exercise, and I told you last time. So corollary, all finite dimensional G representations over K, char K coprime or just 0, coprime with order are semi-simple. So they are direct sum of irreducible. So you just take sub-representation, you decompose it using the this proposition, because sub-representation has a direct split onto a direct sum, and you do it again and again, and you use induction and dimension to make sure that this process terminates. And there you obtain the direct sum of irreducibles. Okay. Now I remind the exact functors. So we have a functor A goes to f of A is, say, left exact if for each exact sequence well, exact sequence I wrote a lot already, so it's let me 0 goes to A, goes to B, goes to C, goes to 0. For each exact sequence, we have 0 goes to f of A, goes to f of B, goes to f of C, and that doesn't go to 0, so it doesn't map surjective maps to surjective map, but maps injective maps to injective maps. Star, this is exact, and right exact when they if the similar exact sequence is exact, but now you don't assume that it maps injective maps to injective maps. Let me give you now examples. Examples are invariance and co-invariance of, and last time I gave example when they are not exact, they are only right exact or left exact. So definition, if V is re-representation, Vg is invariant. The space of invariance is the space of all V inside V such that G of V is equal to V for all G inside the group G. And the co-invariant space no, you don't need it to be finite, really. It makes the same sense whatever group you take. And there is a whole business of invariance theory, which is usually for linear groups. So, coinvariance, the space of coinvariance defined as a quotient V by the subspace generated by all vectors V minus GV for all V inside the space and all G inside the group. Okay, so quotient space, so this is subspace, and it clearly left exact because it's a subspace, so it maps injection to injection. And this is a quotient space. So if you have an vector of C, which is obtained from C, I mean, B is surjectively mapped to C, so the quotient of B is surjectively mapped to the quotient of C. So claim. This is examples of left and right exact functors or exercise. Prove that V goes to Vg is left exact, and V goes to Vg, the coinvariant functor, is right exact. Okay, so this was what we discussed last time, and then we proved that invariance and coinvariance for finite groups are in fact exact. And this is sort of clear for the following reason, that suppose that V, so claim, suppose that V is irreducible. So irreducible representation can be one-dimensional at trivial, in the sense that group acts trivially, or any dimension and non-trivial. Then Vg is equal to Vg is equal to 0 if V is non-trivial.
Sorry.
Yeah.
Maybe it's where's the exercise, maybe the space of variance should go to left.
No, it's a functor.
Ah, okay.
V goes to Vg, and this is also a functor.
Okay.
Thank you. So if V is irreducible, then the invariants are equal to coinvariants are equal to 0 when V is not trivial, and Vg is equal to Vg is equal to V if V is trivial. So the second statement is clear, because if your action is trivial, then this is just everything, and this subspace is 0 because V is equal to Vg. And the first is also trivial because you can't have non-trivial subspaces and you can't have non-trivial quotient spaces. So every subspace is over 0 or everything. And if it's everything, it's V is the action is trivial. If it's 0, then the action is non-trivial. So the first is also clear. And as a corollary, you have that for finite group action, well, assuming the complete reducibility of representations for finite group acting on finite dimensional vector spaces, invariants are coinvariants. I mean, every vector space is decomposed into a direct sum of reducible representations, and then you just take the sub-representations, which is also the quotient representation, which is invariant. And this would give you both of these components. And then, corollary, these functors, v goes to vg, and v goes to vg, are exact. Well, one of them is left exact, another is right exact, but they're equal, so they're exact. In fact, you can provide it explicitly by using the averaging map. It's a projection to the space of invariants. So you can, looking at this map, you can prove this exactness explicitly just by doing a simple calculation. So V goes to Vg, averaging map, takes V, takes a vector V inside V and produces a vector sum 1 over order of G, sum for all G inside G, G of V. This is projection to the space of invariants. So if you have A goes to B, goes to C, goes to 0, you can project using average to A G, goes to B G, goes to C G, goes to 0. So this is already injective because it's invariant, but then it is surjective because this is surjective, so this map is surjective, this is surjective, so this is surjective. This is another way of seeing this exactness of the invariant factor of G invariance, which is probably better because here when we use this decomposition on two irreducibles, we assume finite dimensionality, and here we don't. So probably this is a better way of doing it. Okay, so I'm going to prove the theorem of Emmy-Noether. I mentioned it last time, which is a theorem about the ring of invariants. It's a theorem. Let R be finitely generated ring. Generated ring over, say, C. Doesn't matter actually, over any field of finite of zero characteristic will work. And then you take G finite group acting on G by automorphisms. In other words, you have a homomorphism, group homomorphism from G to automorphisms to the group of automorphisms of R. Homomorphism. Then you can consider the ring of G invariant. The point is that if you have two elements which are invariant under G action, their product is also invariant because G action commutes with the product. So this is a subring inside R is finally generated. Okay. So the plan of the proof, which I'm going to give you, the proof I'm going to give now, but let me first formulate the plan. So plan. First we prove that R G is Noetherian. Second, we consider G action on the polynomial ring, where V is a vector space, which is a representation of G, n-dimensional vector space. Prove that this ring of invariants is finitely generated. This is something that Gilbert, in fact, did, because this was the aim of his work on invariant theory, which is the same paper as where he proved the Hilbert-Nurstein-Zanz and Hilbert-Basis theorem. And finally, we deduce general, so we obtain deduce from C of V the same result for general result for general. Well, it's the idea is that you obtain every ring with an action of G as a quotient ring of polynomial ring with an action of G in such a way that the quotient map commutes with G action. This gives you a way to obtain the result of Noether theorem if you have it for polynomial, obtain it for all rings. Okay. This was the plan. Let's now go to the first step. Yeah, this is another picture of Noether. I think it was like a third or fourth picture of Noether. We will probably have more because we shall do billion theorems of Noether. She was like a founder of commutative algebra. And this is her story, done by Spanish, I suppose, artist, because it has Göttingen, which is Göttingen in Spanish, I suppose. So they say that she says that she was born in Erlangen. She had 3 younger brothers. Not entirely true, I think, but maybe it is. I thought she was born in Göttingen and then she moved to Erlangen or Heidelberg. Anyway, so then she went into Göttingen, was a student of Hilbert, got friends with Albert Einstein. In fact, they collaborated a bit about physics, and Noether has very beautiful results in physics. At some point, Einstein wrote a letter to New York Times, where he said that she is like the biggest genius of the century or something like that. He was extremely high opinion of Noether. Then she migrated to the United States, went to some very strange college and died there. So this is her story. Her brothers were, well, one of them was maybe okay, but she had a brother, Fritz, who was probably maybe even equally good mathematician, except, I don't know, he died younger than Noether because he went, instead of, unlike Noether, who went to States, he went to Soviet Union, and then he was accused in some political crimes and died, was shot by KGB. And he was responsible for the modern Hodge theory, together with Hodge, obviously. So he's a really important guy in math. Unfortunately, all his manuscripts were lost, and then other Soviet mathematicians published them under their own names. Because you can't publish anything by and the name of the guy who was shot by KGB. This is impossible in Soviet Union. Okay, so I am going to tell you this theorem of M in Noether. First, I will do with Noetherianity. So you have an ideal. So claim. Suppose you have R Noetherian, and you have R G inside of R. It has reaction. It's invariant ring, it's a ring of invariance. And of course you have averaging, so G is fine. I think you can't avoid using averaging in this result. Okay. Then RG is also Noetherian. Proof. Suppose you have an ideal inside RG. You can have a bigger ideal, Ri times R. This is an ideal generated by I inside R. It's a bigger ideal. It's a bigger ring, it's a bigger ideal and a bigger ring. But then you can apply the averaging procedure. Of IR is equal to I. This is because if you take element of I and you average it, nothing changes. Element of I is already G invariant. So if you apply averaging procedure to an element of IR, let's write it, of sum of say Pi Ri, where Pi belongs to this ideal, which is invariant, and Ri belongs to the ring I. So this sum will be equal because you can multiplication by pi commutes with averaging because it commutes with the group action. Pi I is already invariant. So this will give you sum over I. Then you take pi I average of Ri. And this gives you I because averaging of Ri belongs to Rg. It's an invariant element, so it belongs to I. Good, so if you have an ideal inside I, you can move it to R, and you can recover it back. So now suppose you have a chain of ideals. I0 goes to, like, strictly increasing chain of ideals. I1 goes to I2, and so on and so forth. And this is all our ideals in RG. This chain gives you another chain of ideals. I0R goes to I1R, inside I2R, and so on. So this chain of ideals was sticked. And this chain of ideals will be also sticked because if it's not sticked, they stabilize, but then these ideals also stabilize because you can recover the ideal IK from IK times R by this argument. So if this was a strictly increasing chain of ideals, you obtain a strictly increasing chain of ideals in R, which is impossible because R is Noetherian. So this stabilizes, then this stabilizes as well. So this proves the first statement of Noether, the first step of the proof that if you have a Noetherian ring, then the ring of invariance is also Noetherian. This doesn't imply finite generatedness because, as I told you last time, there are rings which are not finitely generated but still Noetherian. The best example is probably the example of a ring which is not finitely generated but Noetherian. You take C of this double square brackets of T, it's a ring of formal power series. So you take element of this ring as a sum, AI T power I. You can sum such sums, they're infinite, but it doesn't matter. And you can multiply them formally. It's still possible, but this ring is uncountable dimension because like it contains if you take like all I equal to 1 or 0, then even that is already linearly independent. So it can't be finitely generated. On the other hand, ideals in that ring, so all ideals in R are just generated by T power K because this sum, suppose you have a sum starting from Ki equal K to infinity, AI, so you have a sum AK T power K plus AK plus 1 T power K plus 1 plus and so on. This sum is T power K times something invertible. Sum of from I equal 0 to infinity, I plus K, T power, I plus K, T power I. So AK is non-zero. It starts with a K, then it is invertible because if you have a power series starting with non-zero free term, then it is invertible. So this term is invertible, and this is a generator of an ideal. So in fact, you can prove that this ring is principal ideal ring. It has all ideals are generated by just T power K. They are finitely, well, countably many, but for each sequence of ideals, it has to terminate if it's increasing. There's decreasing sequences don't terminate, but increasing terminates because the number of K should decrease, and it's fine. So the Noetherianity doesn't immediately imply finitely generatedness. We need to work to prove.
Does it work for any formal power series?
The same argument? No, it's not a principal ideal ring. Even for.
I mean, we can take as such an example any formal power series with coefficients many neutrally.
I don't think it will immediately work. It is true, yes, but it's super hard to prove. So it's true that the formal power series coefficient. Oh yeah, it's not very hard to prove that it is Noetherian, right? Right. Yeah, it's not very hard to prove, right? Yeah, so it's not. You're right, right. Thanks. It will work. So for Noetherianity is true for formal power series as well. It's a version of Hilbert-Basis theorem. Okay, but this ring is never finitely generated because its dimension is too big to be finitely generated. Okay, so to go on, I would give you a new definition of a graded ring. suppose let A be a direct sum starting from I equals 0 to infinity, ik. AK is called graded components. K graded components. And this is called graded ring, is a ring, is a graded ring. If A K times AL belongs to A K plus L. In fact, you can do it with any with a vector space indexed by any group or semigroup. So here we consider semigroup of non-negative integer numbers. You can do it with z by 2, with, well, many other groups will work. And people do it. But for us, it will be only graded from I equals 0 to infinity. And also I will usually assume that A0 is our base field. So in most cases, it's just C. So example of graded ring is polynomials. You have C of V is direct sum. Then you take from I equals 0 to infinity symmetric power of V. So it's graded components. Graded, it's like homogeneous where sim I of V are degree I homogeneous polynomials. Okay. So this is the basic example which people use, but there are more. For instance, you can take another example. J star inside A star is a graded ideal if J star is ideal. So A star is graded ring. So when I say I write star or bullet, sometimes people use bullet instead of star. Sometimes they use star. If I do that, I mean graded ring. Is graded ideal if this is an ideal and J star is direct sum of JK, where JK is by definition intersection of A K with J star. So your ideal is also direct sum of its graded components of this ideal. In that case, the quotient is also graded. Quotient is also graded ring. Then A star quotient by J star is a graded ring. This would be another example. For example, you can take any ideal generated by homogeneous polynomials. It will be graded clearly because its intersection with homogeneous polynomials gives generators. So you would have graded ring this way. Another example is consider a ring inside the polynomial ring. So you take direct sum of even polynomials inside the polynomial. Sim 2I, or I equals 0 to infinity, of V. It's even or even degree polynomials. on V. So in other words, if V is a vector space generated by X and Y, this would be polynomials. So this is C V even. So CV even is a ring generated by C. Then you have X square, XY, Y square. Then you have X4, Y2, YX3, X2, Y2, XY3, and Y4, and so on. So it's all even dimensional polynomials are allowed. It's not even clear that it's finally generated, but it would follow if you think of Noether theorem, because this ring is precisely invariance under a map. So this ring, let's call it R. R is polynomials, well, XY, invariance under the group G, where G is Z by 2. It's a group of order 2x on a polynomial ring R taking x to minus x and y to minus y. So this is clearly an automorphism of a polynomial ring, which is equal to 1 on homogeneous even polynomials, and is equal to minus 1 on homogeneous odd polynomials. So its invariant space is precisely the even polynomials. And in the end, what in particular what Noether theorem will give, it will give a finite set of generators for this ring, which is something you can try to do yourself. It's not hard because in fact this is finite generator. So it's x squared, xy, and y squared. But it's not obvious that that is finitely generated. So you have to prove it. Okay. Well, it's almost obvious. So I gave you graded rings and some examples. Let's go on. So claim 1. Suppose that A star graded ring. Oh, sorry, I didn't say what is finite type. So let me tell you that finite type is a ring where each graded component is finite dimensional. So A star is finite type if AK is finite dimensional, so dimension of AK is 0 for each K. So again, this example of polynomial ring or this example of even polynomial ring, they are all of finite type. The space of homogeneous polynomials of given degree and given on a given set of variables is finite dimensional. Okay, so A star is graded ring of finite type. Then A star is Noetherian if and only if A star is finitely generated.
Could you explain how it could be 0?
Sorry?
Could you explain why it's 0?
Oh, 0. Of course not 0. Less than infinity. Thank you. Finite. Thanks. It was a misprint. Sorry. Thanks. Yeah. Okay, good. So suppose that A star is Noetherian, then it is finitely generated. So one direction is clear. So if A star is finitely generated, then A star is a quotient of the polynomial ring, like generated by these generators by some ideal. And it is Noetherian by Hilbert Bayes theorem. So this is one direction. So if we want to go opposite direction, it won't be that difficult either. So this is the, I told you that in general, Noetherianness doesn't imply that, that the ring is finally generated. There are lots of Noetherian rings which are not finally generated, but with this it will work. But before I go, there's a precaution which I have to tell you. There are two finally generated, so the word finally generated is bad. It is used in the entirely different meanings applied to models over a ring and to rings. If a ring is finally generated, this means that it's a quotient of polynomial ring. If a model is finally generated, it's that it is a quotient of a finite. It has a basis essentially. It's a quotient of a free model which is finally generated. So our model is finally generated if that our model M is finally generated if M is Rn quotient by some submodel. And the ring is finally generated if R is C is the polynomials quotient by ideal. So for instance, this thing is like finite rank over R if R is a vector space, and this is countably dimensional over C. So we will use both, but every time you have to realize which of them is used, because for instance, sometimes you consider a ring. You can consider a ring finally generated in the sense of having a finite number of generators, or you consider it as finally generated submodel over a smaller ring. And unfortunately, both senses are valid, and you use both one or another. So you have to always specify when you say finally generated as what it is finally generated, as a model or as a ring. Okay, so this is bad terminology, but it was given. We didn't invent it. It's since forever. Okay. Yeah, so when I say ideal is finally generated, I mean it's finally generated as a model. So step 2. A star is a Noetherian ring. And then you can consider ideal, A bigger than 0, ideal, which is finally generated. Every ideal in a Noetherian ring is finally generated, so you can fix its generators. So we take A1 dot AN generators of A positive, and I claim that they generate A star as a ring. So they're generated as a model. And this is generated as a ring. And I would also assume that I are all graded. If they are not graded, I would just decompose each of these generators onto its graded components, which also belong to this ideal, and I add these graded components to the set of generators. The set of generators will increase, but it will contain the generators which we already have. Okay, so this was step 2. Now I'm going to give you step 3, telling that this set actually generates the ring. So step 3. Generate A over A0, which is C, by our assumption. Okay, consider, suppose it's not, it doesn't generate, suppose there's something which is not generated by these guys. So suppose that Z inside this ring is an element of smallest degree, not generated by these guys, A1 dot AN. But then it is still generated by these guys in the sense of ideals. So Z is sum of AI, Ri, where Ri are elements in A star. This is because this ideal, it belongs to this ideal, because A positive is generated by AI as ideal. Okay. So I have this nice expression. Z is equal to sum of Ri AI, and degrees of Ri are all less than degree of Z, which implies that Z is Ri are generated by our generators AI. And this in turn implies that Z is also generated by AI because it's expressed like that. So the argument is not very hard, but the problem is psychological because you have two notions of finite generatedness and you have to use both. Okay. Is it clear? Please ask questions. So I assume that Z is graded. So graded element. And all these AI are also graded. Graded means that it has pure grade, it belongs to some graded component. But it's still expressed in this form. So AI are graded, so errors should be also graded, yeah? Clear? Okay. So now we can finish the proof of Noether theorem, at least for polynomial invariance. No, it's not that hard, because for polynomial invariance, our ring is thus graded. Okay, so what is polynomial invariance? Suppose you have V is a vector space, and you take G, which is acts on V, and then it acts, G acts on the polynomial ring, on C of V. So what is a polynomial ring? You have a basis, so C of V is a polynomial ring. If you have a basis x1 dot xn in V, this is a ring generated by polynomials on x1 dot xn as considered as a variables. So variables. Now your G action, it takes G of xi is some linear combination, sum of aij, xj, where aij are just numbers. This is your representation of the group on the vector space. It is mapped by matrices. I mean, it acts by matrices. And this, then you just extend this action from V to all symmetric, formal symmetric sums of the bases. So this gives you the action on linear action of a group on a polynomial ring. It's just linear on the set of generators of the polynomial rings. So theorem, suppose that G acts on V linearly, then the ring of G invariants C of V G is finitely generated. Okay, one of the forms of this theorem pretty much everybody knows because it's a theorem about symmetric polynomials. If your G acts on the basis exchanging the variables, this is an example of linear action. And then the invariant part is symmetric polynomials. And it's a course of basic algebra that symmetric polynomials are generated freely by elementary symmetric polynomials, which are finitely many. So we can think of this theorem of Noether as a generalization of this theorem about elementary symmetric polynomials generating polynomials. It's just generalization for any possible group action. That you have finitely many generators of this ring of invariants. So the proof. So you have V C of Vg is graded. This is because G acts on each homogeneous polynomial, mapping its homogeneous polynomial to the same degree. So it's a direct sum of homogeneous polynomials, graded, Noetherian, and finite top. Then it's finitely generated by Noether theorem, which I just gave you. And you even have a set of generators explicitly from this theorem. You just take generators which generate the ideal of positive degree terms. And this would give you also a set of generators for the algebra. Okay. Is it clear? So you have this precisely this claim 1. Okay, and so it's finite type because it's a subring of something which is finite type. It's graded because the action preserves its grading, and it is Noetherian because the ring of invariant elements is Noetherian, as I told in the beginning of this whole long proof. Good. I think we're almost done. Yeah, it's the last slide. Now we can prove Noether theorem. Again, theorem. Suppose that R is not finitely generated. G acts a finite group. which acts, and we'll suppose it's characteristic 0 and characteristic co-prime with order of G would enough. So it's finitely generated group acting on R biautomorphisms and Rg is a ring of invariants. Then Rg is finitely generated. Okay, so proof follows from this theorem about polynomial invariants. And it is really short. So we just obtain this ring as a quotient of polynomial ring. So I mean, this is finitely generated. Take f1 dot fn. It's a finite set of generators. Of R over V over C. And then you take the orbit gf1 dot gfn is the finite set orbit of vectors f1, fn, and R, finite set. And it also clearly generates C because it contains Vi, Fi. So let's call this space V. It's a space generated by this finite set. Then R is the quotient of C of V by some ideal. Okay. Now our G acts on V linearly. Then this quotient R is finitely generated. Okay. On the set on the space V, yeah, because the space V is just finitely dimensional space where G acts like so it maps V to some but I mean so V is not the space freely generated by these guys. It's space inside R, G invariant. So you don't know that this is a basis there. They can be linear relations between these functions. But we know that the space is still fine dimensional and G invariant. This is the only thing we need to apply Noether theorem, because Noether theorem is about rings which are quotient rings of polynomial. Well, it's a, of course, yeah. I'm stepping a bit too fast. Let me do it carefully.
So you apply G.
Yeah. So I.
You said that you could obtain some linear relations.
Yeah. So this was step one. Step one. We obtained that R is, and then your the ring RG is C of V G quotient. Well, let's do this as a second step. So step two. R is C of V by some ideal J. And since a ring is invariant under, V is invariant under group action, G is also invariant under group action, then RG is C of V quotient by J of V, G, and here you have G, because a functor V goes to VG is exact. So it commutes with taking quotients because it's exact. So if you have two vector spaces, and one is, if you have, so you have your exact sequence, J goes to polynomials, goes to R, goes to 0. If you are interested in RG, this would be quotient of C of VG, quotient by JG. So this is this equation map. And now this is step 3. Says that C of VG is finitely generated. It's both sides exact because it's a finite group, and we do it over C. It really, I'm not sure it would be, well, probably it would be true for bigger, for general characteristic, but the proof would be probably different. I don't know. I never thought what happens in bad characteristic. Okay, so C of V of G is finitely generated. Then C of V G quotient by JG is also finitely generated. Because it's, a quotient of finitely generated ring is finitely generated. And this finishes the proof. Okay, so I'm done. Thank you very much, and I see you next week. Thanks. Muito obrigado.